Turning to today's talk, it's my pleasure to introduce our speaker for today. Professor Shri Kulkarni is the George Ellery Hale Professor of Astronomy and Planetary Science at the California Institute of Technology. Professor Kulkarni conducted a number of studies in time domain radio astronomy and galactic 21 centimeter absorption, thereby becoming the first student to have earned a thesis from data gathered at the Very Large Array. Among other notable results, he was involved in the discovery of the first millisecond pulsar. He has spent the past 2 decades as the director of the Caltech Optical Observatories, leading both the Palomar Transient Factory and the Zwicky Transient Facility. After stepping down from this role, he is returning to his roots of studying galactic interstellar medium and time domain radio astronomy. And in that spirit, today he will talk on fast radio burst, what next? With that, I'm pleased to turn it over to Professor Kulkarni.
I hope you heard the sounds, the somewhat unusual choice of music. So when Karen asked me, I said, well, let's hear some real stuff from the sky. And those are actually the radio intensity converted to sound, that's all. There really are low frequency pulses, waves, modes that magnetospheres emit. And I thought if you're interested in fast radio bursts, pulsars, what better way to start off with actual natural sounds. So I'd like to thank Chris Pochenek, Wenbin Liu, Vikram Ravi, and Kendrick Smith for providing me slides and for discussion. Okay, the discovery of radio bursts. So in late 1967, astronomers from Cambridge University announced a pulsed radio emitter, CP1919. Right then, searches were launched for around the world for radio pulsars using the 300-foot GBT, which is now dead. Stalin and Riefenstein discovered a few bursts which are highly dispersed, called the NP 0532, NP 0527. I suspect N is for NRAO and P for pulsars. And NP 0532 was eventually shown to be the crab pulsar at Arecibo. I might add here that, to my knowledge, this is the first application of fast Fourier algorithm and fast Fourier transform done by then Cornell student Dick Lovelace. Over time, the success of the FFT approach made pulsar searches FFT as a routine search technique. So now we jump. Pulsar surveys have been done. Perhaps the biggest survey, one which had a big impact in the last 2 decades, is the Parkes multi-beam survey with 13 beams on the sky. Fantastic machine. So in the archival analysis, Maura McLaughlin and colleagues discovered basically dispersed pulses. They're sporadic, and in some cases they could, by guesswork and algebra, show that they're probably pulsed. And they call them as rotating radio transients, RRATs. Okay, so this analysis continued, and in a search of data towards the clouds of Magellan, Lorimer, Bales, McLaughlin, graduate student Narkevic, and Crawford discovered a single pulse, highly dispersed, with a DM larger than that of what you expect towards the SMC. There's a bit of, it didn't make a huge impact, as you might thought, in 2007. Because it seemed there was a lot of confusion about it. In order to add a bit more, and this is something most astronomers wouldn't know, if you say, well, I use microwave, what is the frequency? Well, it's 2.45 gigahertz. If you go to a big shop, like a cafeteria or something, then that microwave is 915 megahertz. It's useful to know such numbers, especially if you find things in these bands. But a clutch of FRBs from Thornton et al. And the reanalysis, I think, established that these were, anyway, so basically the microwave came in, they're called peritons. They're not immediately identified, but it's one of these red herrings And then the story got cleaned up. The offending microbe was identified in the park's cafeteria and probably sent off to the Smithsonian or something. And but a couple of years later, there are new FRBs which look really convincing. A repeater was found a couple of years later at Arecibo. That is up until then, FRBs were thought to be one shot, classical. ASCAP, in its commissioning phase, came up with a clever idea of fly's eyes. That is, you take all the dishes, point them in random directions, not intersecting, so you can look for very bright FRBs with a larger field of view. CHIME, the giant machine, though built for cosmology, probably has its biggest success in FRBs, came on a couple of years ago. ASCAP began its interferometric mode, which is, of course, a very complex operation because it has a rather large field of view phased array feed, lots of antennas. Then locally, we had a real fast commensal system at the VLA. Practically anyone who's anyone in radio astronomy is now doing FRBs. This is just a collage. And you have all the way from the fast radio telescope, world's biggest single telescope, down to interferometers, low frequency, high frequency, and amazingly enough, a very small sort of a shielded dipole. So it's a dynamic range in this field is very high. Okay, so the essentials of fast radio bursts I've summarized. The daily rate is probably 1700 fast radio bursts over the entire sky with a fluence greater than 2 Jansky milliseconds. So that is the standard unit in this field. You measure the flux peak of the pulse in Jansky and the duration in milliseconds. And so this is the natural product, Jansky millisecond. The pulse widths range from being unresolved, meaning, if you below the instrumental width, below milliseconds, some even fractions of millisecond, to many which are clearly many milliseconds. The 108 FRBs, 128 FRBs we know to date appear to be isotropic, and some show scattering tail, by which I mean there's a sort of what is called as a fast rise exponential decay. This is an exponential tail. And you can see that the width of the tail, the exponential folding timescale, is increasing rapidly with decreasing frequency. And that's a hallmark of interstellar scattering, roughly the width going as the 4th power of the wavelength. Okay, the big development after the discovery of FRBs was the discovery of repeaters, that some of them repeat. And that was done at Arecibo, but CHIME, with its constant daily patrol of the sky as the sky sweeps by, has turned out to be, I would say this is perhaps CHIME's big discovery, is a trove of repeaters. So the current statistics are 20 repeaters or so and about 128 FRBs in total. However, this will change once CHIME publishes their catalog of perhaps approaching 1,000 FRBs. Okay. One of the repeaters turns out to be a binary, in the sense that repeating action becomes more pronounced with a period of 16.35 days. It's already telling you that you're looking at some sort of a binary system, a stellar system which is producing these FRBs. Okay, let's look into the repeaters and the volumetric rate. Well, obviously, if something is repeating, it cannot be involved in a catastrophic event, i.e. supernovae. It's a general rule in radio astronomy, or maybe gamma ray, or all the high energy astronomies. As soon as you find something that's bright, you always, with zero thought, you simply say supernova is the first one. And of course, the same pattern followed in FRB research. I would say the big question really is, are all FRBs repeaters? This is very much an open question. I will come back to it towards the end of the talk. Okay, the volumetric rate locally is 10 to the 5 gigaparsec. I'm jumping a little ahead because we know now the extragalactic. So it's 10 to the 5 per gigaparsec cube per year. And in fact, if you include low luminosity bursts, it may be even 10 to the 7 or even 10 to the 8. This rate is so high that the dominant channel cannot involve catastrophic events. Nonetheless, for reasons I absolutely don't understand, there exists a cottage industry of all sorts of impossible, unlikely, or implausible models with a vain hope, I guess, by the authors that perhaps if they shoot enough models, one of them will turn out to be once in a while an FRB model. Okay, well, the key, as in gamma ray bursts or almost as in any astronomy endeavor, is localization. Here's a collage. It's not complete. It's a field where every few days things are happening, provided by Vikram Ravi, which shows where these bursts come from. Now, the repeater comes from the center of a galaxy, very large dispersion, very large rotation measure. Some of them one of them comes beautiful, resolved into a spiral arm of a galaxy. And the host galaxies are a clue to the progenitors. Okay, we'll come back to that. So let's look at, now we know the extragalactic. Where does all this dispersion arise? Okay, well, if you wish, going from our own galaxy, okay, there's in the disk, and we in fact may have a substantial halo contribution. So just the disk alone may be in the usual units, let's say 25 centimeter minus 3 parsecs, but it could in fact go up what we now call a CGM to about 100, which is a major surprise in general, the IGM and CGM physics that we have learned in the last decade. Then of course is the IGM, and then it may intersect some sort of a halo of an intervening system. So there's a jump there. And then symmetrically, that galaxy has its own halo and its own disk and so on. So it's a little complicated where all these dispersions come from. Okay, so the DM is not a perfect measure of what you really like, which is purely this IGM, because IGM is not as simple as you thought it was. Okay, if you place this on a star formation rate versus stellar mass diagram, it appears that most of these appear in L-star galaxies. It doesn't have to be particularly alarming to make FRBs. They just have to, the main thing you can say is, okay, they're mainly in star-forming galaxies and not in the star galaxies whose specific star formation rate in this case is very low. They don't seem to have come from that. Of course, that's a clue that you're looking at some population 1 object. Okay, so now let's come to galactic FRBs. Okay, because this is an interesting story, literally developed in the last few months. So you have FRBs that are coming from population 1 objects, and it sure be fun to find something in our own galaxy. And of course, the question is, what is the FRB rate? How far can you stretch the luminosity function that you'd have a chance of seeing an FRB within a few years, which is the usual time scale in this business, is a thesis time scale of 3 years. Okay, first year coursework, second year build up, 3 years patiently looking for it. So in 3 years, what is the chance? Well, of course, this is at the time, it wasn't very well known what it is. And the real excitement is that we now have a galactic FRB. But let's step back. So here's like the radio astronomer's phase space diagram. The duration of the burst on the x-axis and luminosity on the y-axis. And these are lines of constant brightness temperature. So, here's the famous 10 to the 12 Kelvin line, which separates objects below 10 to the 12 Kelvin are incoherent emitters. And the ones above that have to be coherent emitters. Or if in some cases, if they're close to it, you can also cheat by invoking relativistic velocities. Okay, but there's no question that far away from that, by the time you get to 10 to the 24, 10 to the 36 Kelvin, these we are looking at absolutely coherent processes. Okay, so the bulk of the pulsars, lie here, typical widths of about a millisecond inside the pulse structure. And occasionally, some pulsars, in particular the crab pulsar, a couple of millisecond pulsars are prolific producers of what are called as giant radio pulses. And Tim Hankins pioneered the technique of studying these things. Some of these pulses, the ones which are the brightest, the highest brightness temperature, they have a duration of only a nanosecond. Okay, so think about this. The speed of light is a foot per nanosecond. That's a convenient unit to remember. So, these things come from a foot by foot area on a neutron star. So in terms of brightness temperature, the FRBs are quite bright, but they have some GRPs, giant radio pulses, competing. They lie in the same line. However, the difference is these are nanosecond, maybe tens of nanoseconds, and these are milliseconds and tens of milliseconds. So it's very, very different. So there's a bit more to this game than just saying they're very bright. They're also very durable on the time scale that we are talking of. Millisecond is much, much larger number than a nanosecond, right? Okay, so now let's come back to the local FRB analog. And I have a little story to tell you. A few years ago, 3 years ago, when I was stepping down, decided I had enough of optical astronomy, came back to radio, met a bright student at Caltech, and I said, look, why do you look like a bright guy? Why don't I take up this project of looking for galactic FRBs? And you work on it for part 1 of your thesis, and if it doesn't succeed, don't tell anyone. And then you could work on DSA, which I knew was Greg Hallinan and Vikram were already pushing hard on that. And on the other hand, if you succeed, tell everyone. But I did tell him the chances were only 10%. Okay, because if there are local FRBs at this end, you can easily detect with a dipole. Okay, so students Chris Bochenek, and he went about, constructed basically cross dipoles with some shielding, Roach boards, analysis, and installed at Goldstone, Owens Valley, and Delta, Utah. And had the fantastic success of actually that 10% became 100%. Okay, but the story for that is the following. So it's 28 April, an amazing day for FRBs. So on April 27th, starting with swift bat, bursts were seen from a soft gamma repeater, 1935 plus 2154. Okay, so our galaxy has about 30 SGRs. Over time, they've become very recognizable and an increasingly dominant contribution to the neutron star birth rate. They may be as frequently born as maybe a third of the total neutron star population. And it's not a particularly outstanding SGR. If you ask me, I would have named a few others actually. Anyway, so next day, CHIME detected a dispersed burst with an estimated fluence of a few kilo Jansky millisecond, consistent with the SGR position. The burst was seen in one of the side lobes, which is why the fluence estimates are uncertain, and you'll soon see it was revised a few weeks later by several orders of magnitude. On the other hand, STARE 2, which is the project that was built by Chris, was explicitly designed to go after such mega Jansky bursts, so there's no correction here. And what Chris found was it was a burst brighter than 1.5 million Jansky millisecond, and it is sufficiently so bright that we suggested in our ATEL that this burst could well belong to the class of extragalactic FRBs. That is at the tail end of that picture I showed you before. So it'll be somewhere over here. Okay, full analysis of the X-ray data shows there's a hard burst coincident with the radio burst. I must say that I'm a little ambivalent about this part because there are many X-ray bursts, this SGR and other SGRs I put out. And the coincidence that happens, but none of them except this one has a coincident radio burst, and or it's very few. So it's not yet clear to me. I found a smoking signal in the X-ray data, though the working assumption is something to do being very hard in the X-ray sense. Okay, well, so here's the diagram where now we have pulsars pulsing away, RADs occasionally blipping, burping around, giant radio pulses, and then you have this FRB on the 28th April, and then the extragalactic FRBs. Well, an observer should always look at a diagram like this, and when you see white space, he or she should say, what can I do to go and discover new stuff? Whereas if you're a physicist, you'll say, why they're clustered here, which is never, in my opinion, not as interesting question as the first one. We'll come back to the phase space towards the end of the talk. Okay, so models. You know, the most amazing thing I find as an astronomer and scientist is we can actually sit and compute and even make sense of things we observe, that the physics actually works. I'm always surprised about that, frankly. Zwicky, who was probably one of the brightest, in my opinion, the three great astronomers of the last century, and Zwicky is one of them. And the other two are not from Pasadena. He says, I soon became convinced that all theorizing would be empty brain exercise and therefore waste of time unless one first ascertained what the population of the universe really consists of. So I certainly belong to the Zwicky school. On the other hand, there's the Mark Twain school, and there's a whole bunch of astronomers who follow that. They believe in the idea there is something fantastic, fascinating with science. One gets such wholesome returns of conjecture out of such a trifling investment of fact. That is, you can make models with almost no facts at all because you don't really have to explain anything. Okay, so much so there's in fact a thing called a theory catalog. It's an amusing concept, and I'll just flash it by. Okay, we'll have 4 pages of ideas of what FRBs could be. Okay, page 1, page 2. You can see some words here like action, okay? And you can also see some things like a black hole and a rock and so on and so forth. Neutron stars, white dwarfs, magnetospheres in the end. Okay. So my favorite on this is that it's a magnetospheric phenomena. There are many theories. There's not a theory talk, and the last person you want to give a talk on anything about theories is me. So this is my favorite thing is that there's some earthquakes, starquakes, which dissipate some energy, and the radio waves come out in a small angle. This seems to me a very plausible idea. Okay, so the near future, I need to wind up now. Almost all radio telescopes have been reprogrammed, rejiggered somehow to go into this exciting field of FRB research. My colleagues locally are building through an MSIP grant, DSA 110, which is 4.5 meter telescopes, 110 of them, with the explicit goal for localization. They hope if it is to in fact seek for funding for DSA 2000, which is 2000 elements instead of 110, and they have their survey speed versus angular resolution. So that DSA 2000 will be both an FRB machine, but more importantly, perhaps it'll be a high-speed mapping machine. The Canadians are playing on their strength. Chime's got a lot of collecting area, so they're developing little chimes, outriggers, in Eastern Canada and at Greenbank, and to do VLBI so that you can do millisecond localization and therefore glean information of where the FRBs come from the host, from the disk, from the nuclear regions, and maybe even from some other types of galaxies. Beyond that, they want to, in fact, go the other way. That is, in fact, more like DSA, that is not cylindrical dishes, which actually are very complicated to deal with, as they're finding out. But to go into the more simpler dishes, and sort of this is a Canadian version of DSA 210. For me, I'm sort of this, I'm sort of thinking, okay, now I need to find another student. And if you know any, please send. It's simple. They have to be independent, and they have to be work harder than me, and they have to be pretty smart. And that's all I'm asking. So there's this Karlstrom dishes in the SZA. This is the old Karma array. So why not use this to look at M31, M82, R220, particularly high frequencies? Okay, so let me end here with puzzles and progress. And because I think I may have taken a bit more time than I had, I'll stop here.
Thank you, Shri, for that very interesting talk. We have a number of questions that have been generated. And starting from the top, can you say a little bit about the extent to which microlensing might be affecting the detection of fast radio burst, or how that might affect FRBs?
Okay, so to start with, I have to tell you that this is a field that, I'm not a mainstream player. So I got some support, and we have Vikram Ravi and the panelists to correct me, and also to fill in a vast amount of FRB literature, which I don't read. So Vikram, I'll hand that question to you. I have my own ideas though.
So I guess you get to correct me in this case. Yeah. So on the I guess the microlensing question is what we're looking at the moment. I think there were some ideas a few years ago led by Julian Munoz and collaborators on trying to constrain the fraction of dark matter that could be in black holes on the scales of 30 to 100 solar masses. And it was shown that with of order 10 to the 4 FRBs, if you didn't detect a single microlensed event, in that you didn't detect multiple pulses with a certain time delay between them, you could exclude even 1% of dark matter being made up by these black holes. If we ignore primordial black holes as a dark matter model, then we're in a bit more trouble, because we now have to worry about significant biases. You also have to worry about the fact that if you're passing through a DLA or some sort of a disk, you are likely to also be immensely scattered. And so the constraints start to become a bit more dicey.
Okay, so let me add to that. So here's my little thing. So when you think of microlensing, mostly people think of what I call as incoherent effects. Okay, so there's two rays, one gets bent one way, the other gets by other way, so they take different time. And so you see two pulses, but there's no coherence on that. But if you're a small enough object, when the two rays actually, they will interfere. So you would in fact see the signature of this microlensing, and this has to be for below a solar mass black hole. You'd actually see the signal will actually have some fringe pattern in it, which will reflect the mass of the object. But this is sort of, I would say, complete speculation, and the usual physics sort was not particularly, we can write papers on that.
Okay. We've had multiple questions about the FRB that displays the 16-day periodicity, and specifically, could you explain a bit more about either why you think it is binarity, or the extent to which precession might be ruled out, or the cause?
Okay, I'm not an expert, but let me give again a simple answer, and again, perhaps Vikram or anyone else who have been loose attending, others who have actually worked on this could say, the simple explanation here is, now that we know at least a big channel of production is magnetars, and there's absolutely no reason to believe that you won't get a magnet and a binary system. In fact, we know many pulsar, neutron star, ordinary star systems, the BE X-ray binaries. There's two pulsars actually with eccentric orbit around a B star. So the idea here would be that the magnetar it gets activated. It's obviously eccentric, because it's not on all the time. And therefore there's a periastron passage, and something in this passage would probably trigger more magnetar activity. I would say this is sort of a qualitatively a simple and probably a reasonably physical model for the source. It's not so clear to me. I mean, to me, this is such a simple and a compelling idea because it builds on things we understand. I've really not given much thought to precession, and if any of the panelists have, I'd welcome to say something.
I'll just quickly argue, or talk a little bit about precession in that certainly the kinds of magnetars that people think can make FRBs are likely to have strong enough magnetic fields that will cause enough for deformation as well as a significantly superfluid core that makes precession almost inevitable. And so certainly I think precession plus the sort of asymmetry of the emission is certainly a workable model to also explain this. But I think Wenbin had some ideas here as well.
Okay, thank you. Could you explain a bit more about the distribution of pulse widths from FRBs, and perhaps reading a little bit into the question, how would they compare with, say, pulsars, RATs, and or giant radio pulses from pulsars?
Yeah, okay. Sorry. Yeah, so can go here and well, pulsars have, when you say there's a pulsar, I know, of course, there's a period, which is a certain time scale, but then those pulsars are very narrow within that period. There are some pulsars whose duty cycle could be as small as 1%, which means they're only on to 100 of the period. And then within that, you have micropulses, and occasionally you can even resolve these micropulses into smaller structures, and of course, finally the finest, for which it has to be bright before you see it as a giant radio pulses. So the pulsar phenomena really extends, I would say, typically from few milliseconds, which is some sort of a collection of micropulses because they do something coherently. Either they drift together or they appear in a certain pattern, down to microseconds, and then the giant radio pulses extend that to another factor of 3, from microsecond to a nanosecond. The FRBs, as you can see from this diagram, while their width is, they seem to be only a factor of 10, between 1 and 10 milliseconds. But we have to be a bit careful when you look at a diagram like this, because broader the pulse, you'll start losing it. I mean, if you take the same fluence and you spread it out over a longer duration, it'll not be easily detected. And equally at the other end, which is the short end, and that's where I think there's some excitement actually, it should in principle be easy to go and look for nanosecond may be a bit hard with all the scattering and so on, but let's say let's say 10 microsecond pulses, okay? So that you're not limited by scattering in at least in some parts of the sky and so on. But those searches, the most searches are currently done sort of incoherently, and therefore with the channel width, inverse of the channel width then sets the scale at which you can see. So if you have a very narrow pulse, it gets diluted by your instrumental broadening. Or if you have a narrow pulse, it gets diluted by interstellar scattering. We should keep an open mind especially on the short end, but otherwise, I'm not sure what these widths are telling you, other than I think they're actually magnetospheric, which is something we see in pulsars. Again, but you have to understand that I'm sort of not a mainstream FRB person, and some of the FRB people will be getting red in their face with this sort of dismissing of emission mechanisms and so on. But let me say one thing, and then Vikram can battle me out. I would say for all the 50 years or 60 years of pulsar studies and emission mechanisms, we have learned nothing. And Joe can jump in too, Alku.
I was going to move to the next question. Actually, just one clarification. We had at least one participant who had an internet hiccup, and could you confirm that the 10 to the 5, the volumetric rate of 10 to the 5 per cubic gigaparsec per year is the number of FRB events versus the sources?
With the current precision, it's the FRB events.
And there was a question.
You know, most of them are dominated right now. Most are still dominated. I mean, as I said, you know, even in the current sample, only 1 in 5, 1 in 6 is a repeater. You can take that out. That number won't change much.
There was some discussion, some of which has been answered live, but some discussion about the nature of the host and specifically the extent to which face-on galaxies might be more common for, at least for spirals. And did you want to expand anything in terms of host galaxies?
I think I don't have anything specific other than so far we have not seen FRBs from elliptical galaxies. That would be very interesting to see one, I would say. So some of this discussion is very reminiscent of the situation for GRBs. So roughly, as I said, you know, the FRBs, whatever the first dozen galaxies, they seem to be occurring in galaxies with star formation, and in this particular case, in the center nuclear region, which for a while had a red herring where every FRB came from AGN. But then you have some odd FRBs like this, okay, which are offset. And is that happening in the halo of that galaxy or in a tiny, you know, star-forming dwarf galaxy? Those are the kinds of questions I would find them very interesting, because they'll be the ones that will give a clue on you know, the lifetime of magnetars, or maybe it's not magnetars at all.
I will take a bit of chair's prerogative and ask about, you mentioned very briefly that no counterpart at another wavelength has been seen yet. Do you expect one to be seen, or are there perhaps physical reasons why we should or should not be looking at specific wavelengths, with of course the exception of the SRG?
Yeah, so this is one of those things where if there's a common sense answer, and that might bite you in the end. And so if you're a real explorer, you shouldn't think of all these theoretical considerations. But let me start with that, because that's something we understand. The energy, the energies, if you really believe this come from neutron stars and ultimately powered by magnetar, the energy store is actually quite limited. So if you try to start pumping into X-rays in a routine, in a big way, it might be very difficult energetically. But having said that, we do know this, at least the one of this FRB of the 28th April had a X-ray emission that was associated with it. It would be very hard to see that from another galaxy. We could see that because, you know, it's in our own galaxy. The rates of FRB, you know, so anyway, the summary of that is the energetics of, unless we identify some other type of source where the energy supply is large, it'll be hard to see. It's hard for me to understand how it'll keep powering at high energies, because the main radio we can get away, main reason we can get away with radio is the energies involved are trivial compared to the scale. However, I do think every time some very smart people have made such arguments, 10 years later, they've been proven to be wrong. when they say everything we know that has to be understood has been understood. So I would view this other way and say optical astronomers should start making time domain surveys which are sensitive to at least seconds or if not milliseconds, because they need to find their own fast optical transients to keep up with the radio astronomers. Otherwise, they'll be stuck with a very slow moving world. But that's where this, on the one hand, on the other hand, is that, when you take bets like this to do new things, you have to figure out the feasibility. I don't think I'll take that bet. If there's a young person, again, I will encourage that person to take a bet for, a certain length of time and not tell anyone about the work. And if they succeed, tell everyone about the work.
There's one that just appeared regarding the galactic FRB or the SRG. It appears that the person is asking why was something like the SRG FRB not detected through the side lobes of something like either the Park survey or perhaps Arecibo?
It's possible. There's no question at all. In fact, this is for a while, let's see. Some SGRs put out giant flares, maybe once in a decade or once in 2 decades. And for a while, the idea that FRBs come from giant flares was really popular. I'm talking just a few years ago. So Shri actually looked at a variety of radio telescopes at the logs because he knew exactly when it happened with a bit of dispersion delay, and convinced himself that there was no such thing. Basically, think of looking at some VLA data. You see a big something, okay. I think the first thing you'll do is probably even have an automated program that just smashes it down because you're looking at some very faint galaxy. And it doesn't make sense to have such a bright signal. And so in that sense, our CHIME colleagues have to be commended that they actually, in some sense, allow for things in the side lobes going to tens of degrees to receive the signal and process it. So, this is a case where the signal is there, but the comprehension is not. It's quite common actually in life and in astronomy. So I would say this is all to, because if you start allowing any such glitch to come through, well, soon you'll have so many microwave, cell phones, what have you come through. So most of the time, these things are rejected because of the large number of false positives that any such thing generates.
A question appeared in the chat window, not the Q&A. The individual asked whether there's anything beyond localization that would allow us to understand the source of FRBs, particularly given if it's difficult to detect them at other wavelengths. Well, anything other than localization. It's an interesting one, I'm thinking. Okay, so the problem you're posing is you won't get any localization, and can we do multi-wavelength or not? Oh, I interpret it as simply, even if we can do localization, that may not be sufficient to provide the nature of the source clearly. So are there other kinds of measurements in radio wavelengths that we should be doing?
Yeah, so I would say the binary repeater is an example where you may not know where it is coming from, but if you have tons of data, okay, and you really find the specific phase is very repeatable, and let's be a little speculative and say FRBs come at a certain pulse phase, which I know I'm making that up. I mean, basically, if you can start figuring out the period of the underlying neutron star from the data. That would be fantastic. I mean, that would be a real big clue, I would say. But right now, there is no reason to believe it. Certainly from magnetars, there's no connection between the phase, the rotation phase of the magnetar and the bursts of the magnetar. So I would say if we had something, the signal has to be in timing. Timing can be a very powerful indicator, but you need to get timing data. So if you see pulses from FRBs, that would be amazing. That would be almost direct. At that point, it explains itself.
What about polarization?
Polarization, I guess if the polarization angle always turns out to be the same in a repeater, that would tell you some. But some polarization swings have been seen, I think, in a few cases, if I'm not mistaken. Isn't that true, Vikram?
Yeah, some swung, some are constant.
Yeah.
Some change from positive. Yeah, you see it.
Yeah, so I know at the risk of annoying the chair, okay, yeah, we've seen polarization swings. We've seen them in pulsars starting in 1968. Okay, so it rotates. I think that's about it. So to tell me a bit more than that, I know if you can figure out some astroseismology, I'm just speculating right now, thinking through. Let's say I see an FRB and I see a lot of ringing there. Some stuff that gradually rings and dies down. Well, maybe I'm probing. It's like earthquakes. If you can detect the earthquakes, you can know a lot of the stellar interior. So maybe if these FRBs are really connected with the star quakes, and if somehow there's an earthquake that rings and it comes back in the FRBs, that would be an amazing neutron star astroseismology.
There's one very interesting question about whether the dispersion measure changes during the burst, or what happens in terms of.
Yes, I believe yes, but I only know because I went to coffee. But it does, Vikram. I believe you had a paper. Am I
wrong? No, I think that was more on the polarization tree than on the dispersion tree.
Isn't there a FRB for? I mean, the repeaters have a dispersion measure changes which are secular, but that's not the question. You're saying, well, that's a little hard one, Jill. Okay, now I understand. So you have a burst, and within that, can you get a DM change? Yes, except you won't know that very much, because here's the problem. What I really didn't talk about, actually, and I sort of made fun of the emission mechanism stuff, but here's something which may be a clue. So I don't have a ready picture to share with you, but you have the pulse is dispersed. Okay, it comes at the higher frequency first and comes at the low frequency later. So in a band, you have this pulse that's dispersed. And the simple idea in the past would have been, yeah, it goes as nu to the -2. The only unknown is the number in front. So let's bash it through least square fit, determine that number. All the pulses in the various bands now line up. But actually, some of the more detailed studies show that they don't line up, actually. I'm talking of the more minute level, okay? Of course, you can fix that by making some changes as a function of time, but I'm not sure that'll be unique nor perhaps physically satisfying. But there are some clues there that the simple model of a broadband pulse that's emitted and very simply dispersed by a cold plasma may not be correct, because after so-called de-dispersion, the standard de-dispersion least square fit gives you a solution, but by eye you can in fact sometimes get better signal to noise ratio. It's not very clear what exactly you're minimizing here. And I won't be surprised, Joe, because magnetospheres do have plasma, so it's not unreasonable actually for there to be some changes. But this would require the FRB to be traveling a lot, so you're actually seeing at different lines of sight. So that might be an interesting venue to study, especially with something like FAST, where you'll have a lot of signal to noise ratio. or maybe you do like chime and DSA. I mean, some really wide band. But the problem with all this stuff is that FRBs, unlike pulsars, are intrinsically not broadband creatures. That is, even within like the 1.4 gigahertz band, even if you have 300 megahertz, you could see FRB emission only in one half of the band, but not the other. Okay, so that sort of complicates things. I'm sorry, it's a long answer. It's an interesting thing to think about anyway.
Well, with that, we should draw to a close as we approach the top of the hour. Thanks, Shri, for a very interesting talk. I think it was appropriate to end on perhaps as many questions as answers. And thanks not only Shri, but to all of the speakers throughout this summer short talk series. It's been a fascinating view of modern astronomy. And with that, I bid you well. May you all stay safe and stay sane.